Welcome back to the deep dive. Today we are doing something a little different from our usual stuff.
Yeah, quite a bit different, actually.
Right, because usually we look at things happening right now, politics, tech trends, history, that kind of thing.
Grounded stuff.
Exactly, grounded. But today I want to look up, and I don't just mean checking the weather. We are looking way, way up.
Into the cosmos.
Yeah, we are talking about the ultimate barrier, the cosmic speed limit, and basically the absolute human obsession with breaking it.
It really is an obsession, isn't it?
Yeah.
Because it's the one number that seems to dictate literally everything in our reality. The constant,
Right.
the letter C, the speed of light.
Which is roughly 300 million meters per second, or about 186,000 miles per second.
Which sounds incredibly fast to a normal person.
I mean, yeah, compared to my commute, it's instantaneous. But here's the problem, and this is really where we need to start today's deep dive for everyone listening. When you look at the actual scale of the universe, light is actually, it's kind of slow.
Yeah, it's painfully slow.
I think that's the existential crisis that every astronomer eventually faces. You realize that the universe is built on a scale that makes light speed look like a total crawl.
It's depressing.
It is. Because if you travel at the absolute limit of physics, that 186,000 miles per second, a trip to our nearest neighbor, Proxima Centauri.
The very closest star to us.
Right, the absolute closest. It still takes 4.2 years.
And just to clarify for everyone listening right now, that is a one-way trip.
One way, you go there, you take a quick selfie, you turn around and come back.
That's nearly a decade.
A decade of your life gone. Just traveling. And that is just the neighbor.
Right, that's like walking to the house next door.
Exactly. If you want to cross our own city, our own neighborhood, the Milky Way galaxy, it takes 100,000 years.
100,000 years. I mean, human civilization hasn't even been around that long.
Not even close. So, even if we build the ultimate ship, the fastest possible thing allowed by Einstein, we are still effectively trapped in our own backyard.
We can see the rest of the universe, but we can't touch it. Unless we cheat.
Right, unless we cheat.
Which is exactly why we have science fiction. To save us from the absolute boredom of multi-generational space travel.
Nobody wants to read a story about people sitting in a tin can for 10,000 years.
No, they don't.
Yeah.
But today, we aren't just looking at the fiction. We have a really fascinating stack of sources here for this deep dive.
A very heavy stack.
Yeah, we've got breakdowns of the classic sci-fi tropes, Star Trek, Star Wars, Dune.
The fun stuff.
The fun stuff. But we are pairing that with some incredibly heavy physics.
The not so fun stuff, depending on how much you like math.
Right. We have transcripts from Star Talk. We've got reports from the Department of Energy on radiation. And this is the crazy part, a brand new paper from the Journal of Modern Physics.
The SIRP paper. Yeah, the SIRP paper. And it claims we might actually be able to build a warp drive without needing the energy of 1,000 suns.
That paper is a massive conversational shift. It really is.
You'll definitely get to that. But you're right, the mission today is to look at how we cheat the speed limit in our dreams first.
And then see if the math actually allows us to do it in reality.
Exactly. So let's start with the dreams. Because let's be honest, if you are writing a space opera, you need faster than light travel.
FTL.
FTL. Otherwise, your story is just people sleeping in pods for centuries.
Or dying of old age before the plot even starts. It's a narrative necessity.
It really is.
If you want a galactic empire, you need a way to govern it. You can't govern a planet if it takes 500 years for your tax collector to get there.
Good luck enforcing those laws. So, in the sources, we have a breakdown of the greatest hits of sci-fi propulsion. And the big one, the one everyone listening probably knows, is the warp drive.
The classic.
This is the Star Trek solution. But I want to be specific here because I feel like the word warp has just become a generic term for going fast.
Yeah, it gets thrown around a lot.
But in the lore of that show, it's very specific, isn't it?
It is extremely specific. And what's interesting about the Star Trek version, historically speaking, is that they actually try to ground it in a bit of theoretical physics.
Okay, so how does their version work?
Well, the concept is that you aren't moving the ship through space at super speed. You are using a matter and antimatter reaction to generate enough energy to create a warp bubble.
Okay, stop there for a second. A bubble. What does that actually mean in this context? Am I talking about like a shield?
Not a shield to deflect lasers, no.
Yeah.
Think of it more like a distortion field.
A distortion field.
Right. The mechanic is that the bubble compresses the space in front of the ship and it expands the space behind it.
Okay, I'm trying to picture this.
Imagine you are standing on a rug. If you want to get to the other side of the room, you can just walk across the rug. That's normal travel. Or you can stand still, reach out, and bunch up the rug in front of you, literally pulling the other side of the room closer to your feet.
Oh, I see. So you haven't technically moved your feet.
You haven't moved, but the distance between you and the destination has shortened.
So the Star Trek ship itself isn't locally moving faster than light.
Exactly. The ship is sitting completely still inside that bubble. It's the wave of space around it that is moving.
And in the lore, the source says a guy named Zephram Cochrane invents this in 2063.
Right, that's the fictional history.
Which is completely distinct from the Star Wars method. I feel like people mix these up all the time, but they are totally different physics. Fictional physics, but still.
Oh, completely different. Star Wars, and Babylon 5 uses this too, relies on hyperspace.
Which is essentially a shortcut.
It's more like a completely different terrain. The idea there is that you leave our dimension entirely. You enter a parallel dimension.
Hyperspace.
Yes, hyperspace, where the geometry of reality is just different. The distances are physically shorter there.
So, if I am driving from New York to LA, warp drive is making the actual miles between the cities shorter. Hyperspace is what? Taking a tunnel through the center of the Earth.
That is a fantastic analogy. You exit the surface map, you go down into a tunnel where the geometric distance is shorter, and you pop back up at the destination.
Okay, that makes sense.
You aren't going faster than light in the tunnel. The tunnel is just a shorter road.
But the visuals in Star Wars, you know, those swirling blue clouds, they always imply it's really dangerous.
Oh, yeah.
Han Solo is always freaking out about the nav computer calculations.
Right, traveling through hyperspace ain't like dusting crops, boy.
Exactly.
The danger in that specific lore is that gravity shadows from the real world leak into hyperspace.
Wait, gravity shadows.
Yeah, things with massive gravity, like stars or black holes in our dimension, cast a shadow into the hyperspace dimension.
So if you just fly blind in the tunnel...
You might bounce too close to a supernova's shadow and get instantly incinerated. That's why they need jump gates in Babylon 5, or precise calculations in Star Wars. Got it. Okay, then you have the third major category from the outline, which is the wormhole.
Right.
This is interstellar. This is Deep Space Nine.
The Einstein-Rosen bridge.
Which is a real theory, right?
It is theoretically one of the most grounded concepts we have, mathematically speaking.
So how does this one work compared to the rug or the tunnel?
In this one, you aren't traveling fast, and you aren't going to a parallel dimension. You are bending our own space-time so severely that point A physically touches point B.
Like the classic folding a piece of paper and punching a pen through it scene?
Every single sci-fi movie does that scene.
Every movie. The guy always grabs a piece of paper and a pencil.
But it works. It's the best visual. You step through the hole you punched, and you are there instantly.
And in pop culture, these can be natural, right?
Yeah, like the Bajoran wormhole in Deep Space Nine. It's just a natural phenomenon, or maybe alien-made.
Or artificial, like the Stargate network.
Yeah.
Exactly. A Stargate is basically just a very fancy door frame that creates a stable wormhole to another matching door frame somewhere else in the galaxy.
Okay, I love that the sources also included some of the more, well, let's call them creative solutions. Did you see the one from Dune?
Folding space.
Folding space,
Yeah.
which sounds like a wormhole, but the mechanism is wild. It's not a machine doing the math. It's biology and drugs.
Right. It's fascinating because in the Dune universe, they realized that computers were too dangerous. The Butlerian jihad and all that lore.
No artificial intelligence allowed.
Zero. So they had to replace computers with human minds.
Which seems impossible for faster-than-light travel.
It is, normally. They use something called the Holtzman effect to actually fold the space, basically doing the wormhole thing.
Okay.
But to navigate it without crashing into a star, you need a guild navigator.
Who is hopped up on spice.
Massive, massive amounts of spice. It physically mutates them, but it gives them limited precognition.
So they can see the future.
They can see all the possible future paths of the ship, pick the one safe route that doesn't end in a fiery explosion, and guide the ship that way.
So it's basically mutated fish people using psychic drug powers to fly spaceships.
That is exactly what it is.
It's completely wild, but it highlights something really important that we usually forget. Navigation at those speeds is just as hard as the speed itself.
Oh, absolutely. Think about it. If you are going faster than light, you literally cannot see what is coming.
Because the light from the obstacle hasn't reached your eyes yet.
You are flying faster than the warning signals. You are literally flying blind into the future.
Which explains why you need a psychic. Or, I guess, if we want to get really bizarre, the source mentioned the spore drive from Star Trek. discovery.
The mushrooms.
The mycelial network.
Yeah, the idea that the entire multiverse is underpinned by this cosmic fungal root system.
And if you tap into it, you can just pop out anywhere.
Which requires a giant space tardigrade to navigate, obviously.
Obviously. I mean, at that point, you're just throwing biology words at a physics problem, but it's fun.
It is fun. And we definitely can't forget the infinite improbability drive from Hitchhiker's Guide to the Galaxy.
My absolute favorite.
It's brilliant satire.
How does that one even pretend to work in the book?
Well, quantum physics actually tells us that there is a non-zero probability of any particle being anywhere in the universe at any given time.
Wait, really? Like, my molecules could just spontaneously be on Mars?
Theoretically, yes.
Ooh.
The probability is infinitesimally small, but it is not a flat zero.
Okay.
So the drive in the book basically jacks up the probability of the ship being at the destination to 100%.
By occupying every single point in the entire universe simultaneously?
Yes. And then when you normalize back to normal reality, you suffer side effects from all that probability shifting.
Like turning into a sofa.
Or creating a sperm whale that falls from the sky.
Curiously, the only thing that went through the mind of the bowl of petunias as it fell was, oh no, not again. And then the source mentions ludicrous speed from Spaceballs.
Plaid trails.
Your brain's ending up in your feet.
It's the perfect satire of how seriously sci-fi takes all these warp effects.
But looking at the list from our sources, there was one method that was called the realist approach.
Right.
And this is in movies like Avatar or Alien.
The don't bother approach.
Yeah, they just don't do FTL at all. They look at the actual laws of physics and say, okay, we just can't break this.
So they don't even try.
So what do they do instead?
They travel at a very high percentage of light speed, but still under the limit.
Yeah.
For example, in Avatar, the ship is called the Venture Star.
Right.
It travels at 70% of the speed of light.
That is incredibly fast.
It's mind-bogglingly fast.
Yeah.
But even at that speed, it still takes nearly 6 years to get to Pandora.
Because space is just that big.
Because space is huge. So the crew has to go into cryosleep.
You sleep, you wake up, and you're there?
Exactly. You haven't cheated physics at all. You just pause your own biology so you don't go crazy from boredom.
But think about the psychological cost of that for the characters.
It's brutal.
You leave Earth, you sleep for 6 years, you spend a year working on Pandora, you sleep 6 years on the way back.
Everyone you knew on Earth is 13 years older.
Are dead.
Yeah. If you do that trip a few times for your career, you become completely unstuck in time.
You are physically 30 years old, but your kids from before you left are now retiring and going into nursing homes.
It turns space travel into a tragedy, not just an itinerary.
Which brings us perfectly to the ultimate wet blanket of the universe, Albert Einstein.
The man who ruined the space opera.
Why exactly does he say no to all these fun ideas? We have the Star Talk transcript here in our sources, and they break down the special theory of relativity.
They do a great job with it.
But I want to get past the dense textbook definition for our listeners. Why is Taki the absolute limit? Is it just that, like, the space wind gets too strong and pushes you back?
No, it's not about wind or friction or anything mechanical like that. It is about the fundamental structure of reality itself. To really understand it, you have to change how you think about motion entirely.
Okay, walk me through this. Treat me like I know nothing.
Imagine you have a speed budget.
A speed budget.
Like money.
Exactly. Every single object in the universe, including you and me sitting here right now, is moving through space-time at the exact speed of light. Always.
Wait, what? I'm sitting in a chair. I'm literally not moving.
You are moving through space,
Right.
but you are moving through time. All of your speed budget is currently being spent on moving from this second to the next second.
Okay, so I am cruising through time at the speed of light.
Right. Now imagine you stand up and you start walking across the room.
Okay.
You are now diverting a tiny, tiny fraction of that speed budget into space. Because the total budget, the speed of light is a fixed number. If you move through space, you must move a little bit slower through time.
Wait, is that just a metaphor?
No, that is literal measurable physics. This is time dilation. The faster you move through space, the slower you physically move through time relative to someone standing still. So if I get in a super fast rocket and I use, say, 50% of my budget to move through space,
Then you are moving through time at about 86% of the normal rate. It's a triangle calculation, Pythagoras style, but that's the gist.
okay, I follow that.
But here's the ultimate kicker. If you try to use 100% of your budget to move through space, If you hit light speed,
I have zero budget left for time.
0. Time stops completely for you.
Time just stops.
Completely. If you are a photon of light, the moment you were born in the core of a star, and the moment you hit a telescope lens on Earth a billion years later,
Yeah.
to the photon, those two events happen at the exact same instant. For light, there is no such thing as time.
That is absolutely mind-blowing.
It really is.
So the reason I can't go faster than light is literally just that there's no more speed left to borrow from my time budget.
Exactly. You've maxed out the cosmic credit card. There is no faster because you are already going at the maximum possible velocity through space-time. You are just steering all of it into the spatial direction. You can't give more than 100%.
Okay. That perfectly explains the time part of the barrier, but the outline also mentions something called mass increase.
Yes.
This is the other major barrier.
This is the engineering nightmare side of relativity. Einstein showed us that energy equals mass. The famous E equals mc squared.
Right, there are two sides of the same coin.
So think about what happens when you try to accelerate a ship. You add energy to your spaceship's engines.
Right, I burn rocket fuel.
Usually at low speeds, that energy becomes velocity. You just go faster.
Sure.
But as you get closer and closer to the speed of light, the universe fights back. You pump massive amounts of energy in, but instead of making you go much faster, that energy literally gets converted into heft, into inertia.
Wait, my ship gets heavier.
Effective mass, yes.
Yeah.
It becomes fundamentally harder to push. The faster you go, the heavier you get. And the heavier you get, the more energy you need to push it even a little bit faster.
It's a vicious cycle.
It's an impossible cycle because at the absolute limit,
At light speed.
yes, at light speed, your mass becomes infinite,
Infinite.
meaning you would need infinite energy to push it.
Which we don't have.
You would need more energy that exists in the entire observable universe just to push a single paperclip to the speed of light.
So you can get to 99.9% of the speed of light if you have enough fuel.
Yeah, but you can never, ever push that final decimal point to reach 100%. You cannot accelerate an object through the barrier. It is physically impossible.
Okay. That seems incredibly definitive. You cannot accelerate through the barrier. The door is padlocked, welded shut, and buried in concrete.
Pretty much.
But, and here's where this deep dive gets really interesting for you listening. There are loopholes, or at least things that look an awful lot like loopholes in the physics.
There are a few very specific exceptions to the rules.
Let's talk about the blue glow.
Ah, yes.
The source material from the Department of Energy talks about something called Cherenkov radiation. And this is explicitly described in the paper as something traveling faster than light.
It is.
How on earth is that allowed if we just spent the last 10 minutes saying it takes infinite energy and is completely impossible?
It is allowed.
Yeah.
Because we have to be very, very precise about our terms when we talk about physics.
Okay, precise how?
Einstein's limit is the speed of light in a vacuum. That 300 million meters per second number.
Yeah.
Empty space.
Right.
But light doesn't always travel through a perfect vacuum.
It travels through air, through glass.
Through water. And when light travels through a dense medium like water, it actually slows down.
Brilliant.
Yes, it bumps into atoms, it gets absorbed and re-emitted, it interacts with the medium. In pure water, light only travels at about 75% of its vacuum speed.
Okay, so light is moving slower. It's caught in local traffic.
Exactly. And in a diamond, it's even slower. It drops to about 40% of its vacuum speed.
The source had a great analogy for this. It said it's like a car going 60 miles per hour on the highway, but then it hits a school zone and has to slow down to 24 miles per hour.
That's a perfect way to picture it.
So light is the car slowing down in the diamond or the water?
Right. But here's the loophole. High energy particles, like electrons that get ejected from a nuclear reactor,
Okay.
they aren't light, so they can zip through that exact same water much faster than the light itself is moving in that water.
So the electron is beating the local speed limit.
It is beating the local traffic. Imagine a race. Light is a Ferrari, but because it's in water, it's stuck in second gear. The electron is a Honda Civic, but the Civic is just flooring it.
So the Civic wins the race through the water.
The Civic wins.
And what happens when a particle breaks that local barrier?
You get a shock wave.
Like a sonic boom.
It is exactly analogous to a sonic boom. When a jet plane flies faster than the speed of sound, the sound waves bunch up in front of it because they can't get out of the way fast enough, and it creates a massive boom.
Right, it shatters windows.
When an electron flies faster than light in water, the light waves bunch up in front of it.
And that creates the blue glow.
Yes, it creates a photonic shock wave. Because of the extremely high energy involved, This shock wave registers in the ultraviolet and blue spectrum of visible light.
So that eerie, incredibly bright blue light you see in photos of submerged nuclear reactors, like the Advanced Test Reactor at Idaho National Laboratory mentioned in the sources.
Yes, the ATR.
That glow isn't just a cool LED lighting effect for safety.
No, that is the literal visual scream of particles breaking the light barrier. It's called Cherenkov radiation.
That is so cool.
Beautiful, and it's incredibly useful. Scientists actually use the intensity of that specific blue light to measure nuclear reactions or to detect cosmic showers hitting the atmosphere.
So you can beat light, provided you handicap the light first by making it run through an obstacle course like water.
Precisely. This is a soft FTL. You aren't breaking the cosmic speed limit, see? You're just beating the local traffic conditions.
Okay, fair enough. That is a fantastic party trick and visually stunning, but it really doesn't help us get to Alpha Centauri any faster.
No, it doesn't help with space travel at all.
Let's go back to the hard stuff then. The vacuum speed limit. Einstein says you cannot accelerate an object up to the speed of light.
Correct.
But what if you didn't have to accelerate?
Now we are entering the realm of the tachyon.
I feel like tachyon is the most abused word in all of science fiction storytelling.
Oh, without a doubt.
Every time the plot gets stuck, it's like, Captain, the tachyon beam is interfering with the shields. Or, we need to reverse the tachyon polarity.
It just sounds sciencey.
But they are a real theoretical concept, aren't they?
They are very real in mathematical theory. The Rand paper we have in our stack is fascinating on this exact topic.
So what is the logic behind them?
The logic is elegantly simple. If the speed of light is a solid brick wall that you cannot cross from the bottom,
From the slow side.
right from the slow side, well, maybe there are particles that just live on the other side of the wall.
Particles that are born fast.
Born faster than light. These are tachyons. The name itself comes from the Greek word tachys, which literally means swift.
So they don't have to accelerate up to light speed, which means they avoid the infinite mass problem.
Exactly. They're created already moving at 2 times, 10 times, maybe 100 times the speed of light.
And the rules for them are just completely backward.
Completely inverted. For us, and the physics term for normal matter is tardions, or slow particles.
Tardions, I like that. We're all just tardy.
We are. So for us, we need infinite energy to speed up to reach the speed of light.
Right.
For a tachyon, it needs infinite energy to slow down to reach the speed of light.
Wait, so for a tachyon, the speed of light is the slow motion barrier it can never reach.
You've got it. It's the exact mirror image of our physics. And the energy curve for a tachyon is totally wild.
How so?
For us, if we lose energy, we slow down.
Makes sense. A car runs out of gas, it stops.
But for a tachyon, as it loses energy, it speeds up. Yeah. If a tachyon has 0 energy, it moves at infinite speed.
That feels deeply wrong. How can something with literally 0 energy move infinitely fast?
It feels wrong because the math requires something incredibly strange to balance out.
I knew there was a catch.
To make the relativity equations work specifically, there's a square root calculation that involves 1 minus the velocity squared over the speed of light squared.
Okay.
Normally, if your velocity is higher than light, you end up trying to take the square root of a negative number.
Which gives you a math error on a calculator.
Right. To fix that error and make the math valid, you have to assume the tachyon has an imaginary mass.
Imaginary as in, like, make-believe? A fairy tale?
No, imaginary as in the strict mathematical concept, the square root of -1, the letter I.
Okay, I vaguely remember that from high school algebra, but I thought that was just a trick for plotting graphs. You're saying a physical object in the real world could have imaginary mass.
Well, calling it a physical object is a bit of a stretch.
Because we've never actually seen one.
Exactly. We've never detected a tachyon. But mathematically, if you plug an imaginary mass into Einstein's equation, the final result for the particle's energy comes out as a normal, real, positive number.
So the math technically allows it to exist.
The math doesn't forbid it.
But what would it even be like to interact with one? The Star Talk transcript had a really great line about tachyon time.
Yeah, Neil deGrasse Tyson was talking about how if you could interact with them, they would seem to fundamentally violate causality.
Causality. Cause and effect.
Right. Because they travel faster than light, from our perspective, they arrive at their destination before they leave their starting point.
The Rand paper mentioned something about how observers would disagree on what the tachyon is even doing.
Yes. A fast-moving observer might view a tachyon event as having negative energy, while a slow observer looks at the exact same event and sees positive energy.
So it's completely subjective depending on how fast you are moving.
It breaks all our common sense rules.
And that brings us directly to the biggest problem with any kind of FPL, the paradoxes.
The paradoxes. Specifically, the tachyonic antitelephone.
Which sounds like an indie rock band from the 2000s, but it's actually a famous thought experiment.
Very famous. Proposed by Einstein, Tolman, and later refined by Benford.
It's the ultimate argument against faster-than-light communication, isn't it?
It is. And this is where we really have to ask our listeners to visualize space and time carefully.
Okay, set the scene for us. Let's do the experiment.
You have two people, Alice and Bob.
Classic Alice and Bob.
Always. They are each in their own spaceship, and they are moving away from each other at a very significant fraction of light speed. Let's say 80% of the speed of light.
Okay, Alice and Bob drifting apart really fast.
Now, imagine they each have a special device that can send text messages using tachyons, so the signal travels faster than light.
Let's say it travels instantaneously, just to make the example easy.
Perfect. So Alice decides to send a text to Bob. She sends the word, hey.
And Bob receives it instantly.
To him, yes. He gets it instantly. But here is the massive problem. Because Bob is moving really fast relative to Alice, his definition of the word now is physically different from Alice's definition.
This is that relativity of simultaneity thing.
Exactly. Observers moving at different speeds do not agree on when events happen.
The source used a loaf of bread analogy for this. Can you explain that?
Yes. Imagine all of time and space is a giant loaf of bread.
Okay.
Alice is sitting still relative to her own ship. She slices the loaf straight down. That single flat slice is her definition of now. Everything on that slice is happening at the same time for her.
Got it.
But Bob is moving rapidly through the loaf. Because of relativity, his slice of now is cut at an angle.
The slice is tilted.
Yes, it's tilted. One end of his slice cuts down into Alice's future, and the other end cuts up into Alice's past.
Okay, I am with you so far. His now is diagonal relative to hers.
So Bob gets the instantaneous hey message from Alice. He immediately types out a reply, sup, and hits send. He sends that reply via his tachyon transmitter.
Also instantaneously.
Yes. But because he is sending it along his tilted slice of Bob. Now that instantaneous signal actually travels back into Alice's past.
Wait, so physically, in reality, Alice gets the reply from Bob before she even sent her original message?
Yes. The math dictates that Alice receives Bob's reply of soup a full 5 minutes before she actually decided to pick up her phone and text him, hey.
Which completely breaks the universe.
It shatters it.
Because what if, after getting Bob's reply from the future, Alice decides, you know what, I'm actually not going to text him. I'll just put my phone away.
Exactly. Then Bob never got the message to reply to.
Yeah.
So it never sent the reply. So Alice never received it.
But she did receive it.
Right. You have just created a closed causal loop, a grandfather paradox.
Effect preceding cause.
Yes. And physics usually protects causality fiercely. It is the golden rule of science. Effect absolutely cannot precede cause.
So if tachyons allow you to break that golden rule,
Then most physicists believe that tachyons simply cannot exist.
or at least if they do exist in some weird math way, they can never be used to transmit actual information.
Exactly. Because if you can send a signal back in time to alter an event, reality collapses into paradox.
So let's recap where we are right now for the listeners. We can't go through the light speed barrier normally because it requires infinite energy and makes our ship infinitely heavy.
Right.
And if we try to jump over the barrier using imaginary math particles like tachyons, we break time itself and create universe-ending paradoxes.
Pretty much.
It is looking really, really bleak for our weekend trip to Alpha Centauri.
If you are relying on conventional propulsion or magical particles, yes, FTL is completely dead in the water.
But we haven't talked about the engineering solution yet, the one that bypasses the moving through space problem entirely.
The Alcubierre warp drive.
Yes. This is the part of the source material I was most excited to get to.
Because it is the holy grail of FTL research. It really is.
Why is this one so special?
Because it doesn't try to break the speed of light locally. It actually respects all of Einstein's rules about causality and mass. It just exploits a massive loophole in general relativity.
This is the moving space, not the ship idea we talked about with Star Trek.
Yes, a physicist named Miguel Alcubierre formally proposed the math for this in 1994.
So this isn't just sci-fi writers making things up.
No, this is peer-reviewed physics. Think back to our surfer on the ocean analogy.
Okay.
The surfer is not paddling at 30 miles an hour to catch a wave. The surfer is practically stationary relative to their board.
Right. They just sit there.
It's the wave itself that is moving the water and carrying the surfer along.
So in this scenario, the spaceship sits inside a bubble of flat, quiet space.
Correct. The interior of the warp bubble is totally normal space-time. Inside the bubble, you are floating in zero gravity. Your clock is ticking at the exact normal rate.
So there's no time dilation.
Zero time dilation.
That is a massive benefit. No interstellar movie situation where you go for a quick trip and come back to find your daughter is an old woman on her deathbed.
Exactly. You age at the exact same rate as the people back on Earth.
But if the ship isn't moving, how do you get anywhere?
The wall of the bubble is doing all the heavy lifting. In front of the ship, the drive mechanism violently contracts space. It literally squishes the miles down into inches. This is positive curvature.
Okay.
And behind the ship, it radically expands space. It pushes the destination closer in front and violently pushes your starting point away behind you. This is negative curvature.
So the ship essentially gets pushed forward by the expansion behind it and pulled forward by the contraction in front of it.
Yes, and because space itself, the actual fabric of the universe, can expand and contract faster than light.
Wait, space can expand faster than light?
Oh, absolutely. We know this for a fact because the universe did exactly that during the cosmic inflation period right after the Big Bang. Space expanded far faster than the speed of light.
I didn't know that.
Yeah, the speed limit only applies to things moving through space, not to space itself.
Mm-hmm.
So the warp bubble can move across the galaxy at any speed you want. 10 times light speed, 100 times.
And the ship inside never feels a thing.
No g-forces, no infinite mass. It's perfectly safe inside.
It sounds totally perfect. It solves
Yeah.
time dilation. It solves the infinite mass problem. It avoids paradoxes locally. So the obvious question is, why aren't we building the USS Enterprise right now?
The negative energy problem.
There's always a catch. I knew it.
To make space expand behind the ship, the standard math of general relativity dictates that you need a form of energy density that is physically less than zero.
Less than zero.
Negative energy. Or exotic matter.
How can energy be negative? Energy is just energy.
That's the problem. Normal gravity attracts. Positive mass pulls space inward, curving it like a bowling ball on a mattress.
Right.
To make space violently expand, to push it outward, you need a repulsive gravity. You need negative mass.
And does negative mass actually exist anywhere?
In incredibly tiny, microscopic quantum amounts, maybe. Things like the Casimir effect show tiny, fleeting hints of negative pressure between metal plates in a vacuum.
But not enough to build a spaceship out of?
No. For a functional warp drive, the original calculations done by Alcubierre were incredibly disheartening.
How bad were they?
They suggested that to build a warp bubble big enough to hold a very small ship, you would need an amount of negative energy roughly equal to the mass of the entire observable universe.
You've got to be kidding me.
Roughly 10 to the 62nd power joules of negative energy.
Okay, so totally, laughably impossible. It's basically saying, sure, you can build a warp drive, just condense the entire universe into your fuel tank first.
Exactly. It was mathematically sound, but physically absurd.
But scientists kept working on it, right?
They did. Over the years, other physicists refined the math. They realized you could optimize the shape of the warp bubble. They got the energy requirement down to the mass of Jupiter.
So pretty big.
Then down to the mass of the Voyager probe. But the fundamental hurdle remained. We still have absolutely no idea how to get any significant amount of negative energy. It's a substance that might not even exist in bulk reality.
Until this new paper, and this is the part of the deep dive I have been waiting for since we started.
This is where we get to the SCRP source material.
The paper published in 2025 in the Journal of Modern Physics, titled Exploring the Alcubierre Warp Drive Ship.
This paper is genuinely exciting because it proposes a completely different mechanism to create the space-time curvature.
It completely bypasses the need for negative energy.
That is what the author claims.
How? Because the paper talks about something called generalized gauge transformations. Now, to a layperson, that sounds like pure Star Trek technobabble.
It does sound like something Geordi LaForge would say to fix the warp core.
Exactly. So break that down for us. What is a gauge transformation?
Okay, let's simplify it. In modern physics, we use fields to describe the fundamental forces of nature. Gravity is a field. Electromagnetism is a field.
Like magnetic fields around a magnet.
Right. And usually we treat these fields as completely separate things. They don't really talk to each other directly in the math.
Gravity is the bowling ball on the rubber sheet bending space. Electromagnetism is magnets attracting each other.
Right. But this paper argues that under a specific mathematical framework called a generalized gauge transformation, you can actually convert the properties of one field into another.
Convert them.
Yes. Specifically, the paper outlines a method to convert electromagnetic energy directly into the Wild tensor.
Whoa! Okay, you lost me again. The Wild tensor is what?
Sorry, the Wild tensor is the mathematical description of how space itself curves and stretches. It is the geometry of the rubber sheet.
Okay, so let me make sure I'm following this. Instead of finding magic negative matter to bend the space behind the ship, this paper says we can use high-powered magnets.
In a vastly oversimplified sense, yes.
That is wild.
The proposal is that by manipulating very specific, incredibly powerful electromagnetic fields in a toroidal shape, a donut shape, around the ship, you can literally trick space into curving.
Trick space.
Yes. Think of it like this. Usually, to curve the rubber sheet of space-time, you need to place a heavy rock on it. Mass.
Right, normal gravity.
But this paper's math suggests that if you pull on the very threads of the rubber sheet itself with enough specialized electromagnetic tension, you can create that exact same divot, that same curvature, without needing the rock at all.
That sounds so much more doable than finding negative matter. We know how to make electromagnetic fields. We build supermagnets all the time for MRI machines in hospitals, or for particle colliders like CERN.
We absolutely do. It shifts the problem from a fundamental physics impossibility to an engineering challenge.
And the energy calculation in the paper? This is the real jaw-dropper from our sources.
It really is.
They calculated the energy needs for a 20-meter diameter ship.
Which is a decent-sized shuttle.
Yeah.
Big enough for a small crew to live in comfortably.
Right. Remember, the old calculation for a ship that size was the mass of the entire universe. Then they got it down to the mass of Jupiter. Using this new electromagnetic conversion method, the energy requirement is estimated at roughly 5 megajoules.
5 megajoules.
Wait, stop right there. Give our listeners a comparison. What exactly is 5 megajoules of energy in everyday terms?
It's almost laughable. It is roughly equivalent to the energy stored in the battery of a standard Tesla Model S.
You are kidding me.
I am not.
We went from needing the mass of the universe to power the drive to needing a literal car battery.
That is exactly what the math in this new paper suggests.
That is unbelievable.
Now, hold on a second. I need to be the wet blanket expert again.
Please, go ahead. Ruin my dreams.
That 5 megajoules number is strictly the total energy requirement, the amount of raw power needed to bend the space.
Right.
However, the engineering requirement to create the incredibly specific, hyper-complex electromagnetic field geometry necessary to convert that energy into space-time curvature.
Yeah.
We have absolutely no idea how to build that device.
Oh.
It's basically like saying, well, to build a functioning nuclear bomb, you really only need a few kilograms of plutonium.
Which is true.
It is true. But designing and building the precision explosive lenses and the trigger mechanism to actually make that plutonium compress and explode, that is incredibly difficult engineering.
So we have the fuel estimate, which is tiny, but we don't have the engine blueprints yet.
Exactly. We know how much gas it takes, but we don't know how to build the carburetor.
But even with that caveat, it completely changes the problem fundamentally.
It does. It changes it from physics completely forbids this because the fuel doesn't exist to we just need to be smart enough as a species to build the right engine.
It moves FTL travel from the impossible bin on the desk over to the difficult engineering problem bin.
That is a massive paradigm-shifting shift.
I do have to ask one big question, though.
Shoot.
If we actually figure out the engineering and we build this Tesla-powered electromagnetic warp drive,
Yeah.
do we still have to worry about the paradoxes we talked about earlier?
The tachyonic anti-telephone.
Exactly. Does this warp drive allow me to warp back to yesterday and change history?
It's a great question, and the paper actually does touch on this at the end.
What does it say?
It openly admits that, mathematically, any faster-than-light travel method, even an Alcubierre drive, theoretically allows for the creation of closed time-like curves.
Which is the physics term for time loops.
Right. So the paradox danger is definitely still there in the equation.
That seems bad.
But the paper suggests that nature has a defense mechanism, something proposed by Stephen Hawking called chronology protection.
Chronology protection, what is that?
The idea is that the universe actively defends its own timeline.
How? Like time cops?
More like quantum static. If you try to pilot your warp-ship in a specific curve, that would create a time loop.
Say, aiming for yesterday.
Right. As you approach the threshold of traveling into the past, Vacuum fluctuations, basically microscopic quantum noise, would rapidly build up on the horizon of the warp bubble.
And do what?
The noise would amplify infinitely and instantly blow out your engine, or destroy the ship entirely.
Wow, so the universe would literally break the ship before the ship could break history.
Essentially, yes. You could fly to Alpha Centauri completely safely, faster than light, but the moment you tried to curve the path to arrive back at Earth yesterday, the quantum feedback loop would fry your systems.
The universe's physical way of saying, don't be naughty with the timeline.
Precisely. It cleverly preserves causality while still allowing for deep space exploration.
Honestly, I can live with that compromise.
Most people would.
I don't need to go back in time to kill Hitler or invest in Bitcoin in 2010. I just really want to see the rings of Saturn up close without it taking 3 to 7 years.
And this paper strongly suggests that day might be a lot closer than we ever thought. If this electromagnetic to gravity conversion holds up to peer review, and if we can figure out the engineering experiments,
We are quite literally on the verge of the interstellar era.
it's not just sci-fi anymore.
It is incredible to think about. We started this deep dive talking about how we are fundamentally trapped in a tiny box by the speed of light, that 4.2 light-year prison sentence just to reach the nearest star.
The existential dread.
Yeah, and we are ending the conversation with an actual mathematical blueprint that says the door might actually be unlocked. We just need to figure out how to turn the handle.
That is the absolute beauty of physics. It puts up massive, seemingly impenetrable walls, but it always seems to hide keys if you look hard enough.
That is a perfect final thought for you listening at home.
Thanks.
So tonight, when you go outside, look up at the stars. Try to find Alpha Centauri.
It's down in the southern hemisphere, for those looking.
Right. It is 4.2 light years away. It feels like an infinite, impossible distance. But maybe, just maybe, for our grandkids, it will be nothing more than a long weekend trip.
Just remember to tell them to pack a charger. They'll need at least 5 megajoules for the ride.
I'll make sure they bring an extra battery. Thank you all for listening to this deep dive. Keep looking up.